Hi, everyone. Hope you're all feeling well and dealing with this unprecedented situation. Okay. Personally, I'd rather be back at work, carrying on, but here we are, online, and I'm going to carry on anyway. Basically, I'm going to lecture first. I'm going to show you some demos, some virtual demos here, and talk about some stuff that sort of lays the groundwork rather for simple harmonic motion. And then I'll go to a different format on my iPad where that'll be a different video. I'll share I'll solve some problems and just do some example problems basically on the iPad, so you can look at those two as you work through your first fully online problem set here, taught online and served up online. Anyway, so hopefully it'll go well. The big difference is it's just a lot more. It's just a lot more valuable to see people, I think, look you in the eye and see your wonderful faces, and for you to see my wonderful face and all the rest. But that's not really the case here. So we will forge on anyway. Now listen, this is chapter 11, vibrations and waves, and basically we're going to study things that vibrate, and we are going to study how they vibrate, the energy changes that happen when they vibrate. We're going to take a look at the force requirements for vibrations and the period and the frequency of the vibrations and the amplitude of the vibration. And so we'll cover a lot of that right here, right now. I'm going to try to be relatively quick about this. But lots of things vibrate, right? So lots of things vibrate. Masses on springs vibrate up and down. If you hung a little weight from a rubber band, it would bounce up and down. And I don't know, flies caught in spider webs vibrate. And cars, when they go over bumps, they vibrate slowly due to the springs that are in their suspension systems. Other things vibrate. Guitar strings vibrate. Violin strings vibrate. And they vibrate really well. And the thing about a vibration is they're generally quite predictable. There are vibrations that aren't predictable, but we're not going to look at that. We're going to look at predictable vibrations, and basically predictable vibrations are known as periodic vibrations, where the period is consistent and the frequency is consistent, and we are going to take a look at what is known as simple harmonic motion. And things that are capable of simple harmonic motion are some of the things I just mentioned: the guitar string, the spider web, etc. But also columns of air inside of a musical instrument. They can vibrate in a simple and harmonic fashion and give us nice true tones. Lots of things can vibrate in this fashion. In fact, anything that obeys Hooke's law will exhibit simple harmonic motion. So, quick review. What is Hooke's law? Hooke's law is simply this: that if I pull a spring out of equilibrium some distance, maybe 0.2 meters or so, that takes 20 newtons of force on this 100 newton meter spring. 20 newtons of force will stretch the spring 20 centimeters. Well, to stretch it 0.4 meters, I need twice the force. To go to 0.4 meters, I'm a little bit over it there, but I need to stretch it twice as far requires twice the amount of force. So that's Hooke's law. That is that the force applied to the spring is proportional to its displacement from its rest position, or in the proper parlance, from its equilibrium position. Now, it's not just stretches; it's also compressions. Right? If I compress the spring 0.2 meters, or so, it takes 20 newtons of force to push it to the left. And if I want to compress it twice as far, to 0.4 meters, I need to press it twice as hard. That's Hooke's law in a nutshell, that if you push or pull an object that obeys Hooke's law out of equilibrium, out of rest position, it takes force. And to push it or pull it out of it twice as far from equilibrium would be twice the force. And 3 times as far would be 3 times the force, etc. So for an object to exhibit simple harmonic motion, it must obey Hooke's law, and pretty much all solids will obey Hooke's law, as will other states of matter. Air, I mentioned air. Air will obey Hooke's law. Air is compressible and springy, and it'll obey Hooke's law. But let's carry on here. What can obey Hooke's law? I'll show you a very surprising example in a minute. I think everybody here has no trouble believing that a hanging weight on a rubber band will vibrate up and down, and that a guitar string will also vibrate up and down in a periodic and predictable fashion. But I'm going to show you a quick video right at the end of this little talk here of something that is still to this day to me very surprising, but something very large and unexpected obeying Hooke's law, and we'll dig into the mathematics of it later. But let's switch to this right here. This is a really good example. This is a really classic example of simple harmonic motion. It's a mass attached to a spring on a frictionless table, right? And so when I set this thing running, notice this is not in equilibrium position right now. The initial spring stretch is 5 units, whatever the units are, I'm not quite sure. Perhaps 5 centimeters or something like that. Right. But it's at 1, 2, 3, 4. Well, that's interesting. It looks to be at about 4, just by these hash marks, but that's okay. This is at full stretch right now. That's the equilibrium position. And you'll notice right now, the kinetic energy is at 0, okay? And the potential energy is at maximum because the spring is stretched out as far as it's going to go. Now, let's get this thing vibrating. And so there it goes. It's vibrating through equilibrium. So that's its rest position. And it's compressing the spring equal distances in each direction, 5 units out of equilibrium to the left and 5 out of equilibrium to the right. And so it's vibrating between the two amplitudes, as they're called. So what is amplitude? Amplitude is the maximum stretch from equilibrium. So there it is right there at full amplitude. Right, so they're calling it 5 units. We could change that if we wanted to, but we'll just leave it. So this is at full amplitude right now. And if this is where we started, if we let it go to 0 equilibrium, right about there, let's go back a little bit. Right there, it's at its rest position. The spring is at its rest position. Notice there's no energy, no potential. That's a U right there. It's hard to see. There's a potential energy right there is at 0 because there is no potential energy. The block is at maximum velocity right here, and so it has maximum kinetic energy, but the potential energy is at 0. And the opposite is the case at full amplitude. At full displacement from equilibrium, right there, say, almost full, right about there is full equilibrium, full amplitude, full compression of the spring. You'll notice the block has come to a stop, so there's no kinetic energy. And where's the energy? It's all in the spring. And as it goes through its rest position, the potential energy goes to 0 because the spring is relaxed, but the block is moving fastest. So as we run this, we see, of course, that it slows to 0 at the maximum displacement, but it's going fastest at 0. So we've got maximum kinetic energy as it vibrates through the equilibrium position, and you've got maximum potential energy when it's at either of the two displacements, full displacements. So whether it's compressed or stretched. This is really interesting stuff here. Here you can see the energy vibrating between kinetic energy and potential energy. When it's going through the middle, it's all kinetic, right? Just about in the middle there. And it's virtually all kinetic energy. A little bit of PE there because I'm not quite at 0. There's a little bit of energy in that spring. And when it gets to full displacement, the energy is all PE in the spring, and kinetic energy at full displacement, kinetic energy goes to 0. Again, this one's not quite at full energy. There it is. Full displacement. There it is. Right. So that's worth looking at. Over here, here's the kinetic energy going to a maximum, and notice the potential energy is at 0. When K is at 0, when K is at maximum, U is at 0. And when U is at a maximum value, when the spring is fully compressed, the kinetic energy is at 0. Right? So this is at the end at the full displacement from equilibrium, and this is passing through the equilibrium position. You'll notice if you go up this line here, when there's maximum kinetic energy, where's the thing? Oh, its amplitude is 0. That makes sense. It's going right through x equals 0 when it's got full kinetic energy. Its amplitude is 0. Its velocity is a maximum, and its displacement from equilibrium is 0. Let's go over here. Maximum displacement. You have 0 velocity. That's where the block is right now, at maximum displacement. At maximum displacement, you have 0 velocity. You have full amplitude. You have full energy stored in this spring, and no energy in K. You know, this small a, actually I just called it amplitude, and what I said is true. Everything I've said is true, but this is also, I think this is meant to be acceleration, come to think of it, right? When it's at the 0 point, right? When x is 0, when it's going through the center, there's no force on it, right? When the block is here, there's no force on it because the spring is relaxed, so there's no acceleration. And then as it goes to the ends, right? So where's this thing now? It's at x maximum. So it's right about here, right? It's at x maximum, and so it's got maximum force on it, but 0 velocity. But look at this, the acceleration is maximum because it's got the most force on it. So even though it comes to rest, it's at that point it's got the most. It really goes through rest. It doesn't sort of hang out there. It's sort of like our argument of the ball being thrown straight up. It goes through 0 meters per second, but it doesn't actually stop at 0 meters per second. It passes through 0. It passes right through 0 meters per second, and so and it changes direction. Right? So it's got a velocity here of negative, and it goes positive, and that's where the maximum acceleration is occurring, where the maximum force is occurring, and the maximum force occurs with the longest stretch or the biggest compression. So there's a block bouncing back and forth, simple harmonic motion. I'll speed it up a little bit. I'll see how fast this thing can go, and we'll run it. And what we're seeing is the energies swapping places. The block is exhibiting simple harmonic motion. Now let me say this out loud. The time required to go from full displacement back to the same position, that's called its period. Okay? So from here, click, to here, click. If we timed those 2 clicks, that would be the period of this block, and that would be the inverse of its frequency. I'll write some of that down for you on the iPad in just a few minutes. But this is a good example of simple harmonic motion, and it is periodic, it is predictable, and it is amazing that so many things can exhibit simple harmonic motion, including this very surprising simple harmonic oscillator. This is the Tacoma Narrows Bridge in 1940. There wasn't even a very strong wind that day. It's just that, well, we'll discuss what happened with regards to the waves, the waves, standing waves that got set up in this bridge. But this bridge is exhibiting simple harmonic motion, and that is because the displacement from equilibrium is proportional to the force back towards equilibrium. So when it got pushed out of equilibrium by the wind, it pulled itself back towards equilibrium. It went through equilibrium like that block did, went the other way, out of equilibrium, back and forth through equilibrium. And you can probably guess what happens in the not very distant future. Total collapse. You can't do that to those materials for too long before they fail. No people were injured. Luckily, during this bridge, nobody was injured or hurt or killed or anything. But it was a real turning point in bridge design, and we'll talk about that later. But so that's our first little look at this business here of simple harmonic motion. And I'll do a couple of example problems for you, and you can go do your Pearson, and we will carry on. Okay, have a good day. Take care.